This paper presents the winning solution for the AI Mathematical Olympiad Progress Prize 2, or AIMO-2, competition. The team, including researchers from NVIDIA, developed a recipe for building advanced mathematical reasoning models based on three main pillars. First, they created a large-scale dataset called OpenMathReas, which includes 540,000 unique high-quality math problems, many at the Olympiad level, along with 3.2 million long reasoning solutions. Second, they introduced a method to integrate code execution into these reasoning models through an iterative process of training, generation, and filtering, resulting in 1.7 million high-quality tool-integrated reasoning solutions. Third, they built a pipeline to train models to select the best solution from multiple candidates, improving on simple voting methods. The introduction highlights recent progress in large language models for complex tasks like Olympiad-level mathematics. These models have improved by allowing more tokens for thinking before giving a final answer. Early approaches used chain-of-thought reasoning, where models generate step-by-step solutions. More advanced long reasoning models can now reflect on their work, explore different strategies, and refine ideas within a single output. This has led to better performance in math, coding, and science. The AIMO-2 competition tests models on 50 difficult, national-level math problems that were never published online, making it a rigorous benchmark. The team's submission solved 34 out of 50 problems on the private test set, earning first place. To achieve this, they addressed limitations in existing models by focusing on creating a large-scale dataset. In Section 2, they describe building the OpenMathReas dataset. They collected an extensive set of math problems from the internet and used an LLM-based pipeline to extract and refine them, resulting in 540,000 unique problems. Then, they generated 3.2 million long reasoning chain-of-thought solutions by prompting models like DeepSeek R1 and QWQ32B. They trained Qwen 2.5 base models on this data, achieving state-of-the-art accuracy on benchmarks like AIME and HMMT competitions. For example, their 32B model surpassed most open-weight models of similar size, though it was slightly behind QWQ32B. Figure 1 in the paper shows accuracy improvements across different model sizes. For 1.5 billion parameter models, accuracies range from about 31.6% with a basic COT approach to 65.6% with their OpenMath Nemotron method. For larger models up to 32 billion parameters, accuracies reach up to 76.6% when combining tool-integrated reasoning and generative selection. This demonstrates how their dataset and techniques boost performance. Moving to Section 3, they tackle tool-integrated reasoning, or TIR. This involves combining long reasoning with code execution to solve problems more effectively. Their initial tries to prompt existing models like DeepSeek R1 and QWQ32B for TIR failed, likely because these models were heavily trained on standard reasoning formats and not enough on instruction following. To fix this, they started with a small-scale fine-tuning of an instruction-following model. They built a pipeline that prompts this model to generate long reasoning TIR solutions, followed by aggressive quality filtering to ensure only the best ones are kept. This process iterates through training, generation, and filtering multiple times, ultimately producing a dataset of 1.7 million high-quality TIR solutions. This allows models to not only reason step by step but also execute code as part of the process, making them more accurate for problems requiring calculations or simulations. In Section 4, they introduce Generative Solution Selection, or GenSelect. This is a pipeline that trains models to pick the most promising solution from a pool of candidates. It's an improvement over basic majority voting, where you just take the most common answer. With GenSelect, the model evaluates and selects based on quality, leading to significant accuracy gains. For instance, in their experiments, GenSelect outperformed majority voting baselines on the benchmarks. The paper combines these elements to train a series of models that achieve top results. They provide comparisons showing how their methods stack up against others, like DeepSeek R1, in terms of pass-at-1 accuracy for chain-of-thought and enhanced versions with TIR and GenSelect. Finally, to support further research, the team is releasing their code, models, and the entire OpenMathReas dataset under a commercially permissive license. This includes the 540,000 problems and associated solutions, making it easier for others to build on their work. Overall, this approach demonstrates a comprehensive strategy for advancing mathematical reasoning in AI, from data creation to sophisticated training techniques, setting new standards in the field.